So today I want to introduce this concept called conditional probability. And so in engineering problems, or even in a lot of real-life problems, we're often faced with the question of what's the probability of X given that I observed this thing Y that happened, right? So any kind of diagnosis problem, right? What's the probability that the patient has the disease given that this test came back positive? Or what's the probability that this picture, this blurry surveillance camera picture, represents the suspect that I'm trying to find? Okay, so I get some piece of information and it modifies the probability that I had before. Okay, so this is a really critical probability concept. So mathematically, we represent this concept of conditional probability with a symbol called A given B. So I have two events, A and B, in my sample space, and remember that this region here is A intersect B, right? And what I want is the probability of A given B. And so when you see this vertical bar, you should read in your head given, okay? Well, I look at this picture and it kind of stands to reason saying, okay, I'm telling you that B happened, right? So given that, what's the probability that A also happened? And here I can see that it's just saying, okay, I've kind of now got a reduced sample space. I've kind of confined my sample space to just B. And I can see now that I'm asking kind of the proportion of B that is made up by A intersect B, right? So that's just by kind of visually looking at it, probability of A over B divided by probability of B. It's like how much of all of B is made up of this red area that also includes A. So this critical definition is all you're going to need, okay? And this is just a caveat that as long as the probability of B is greater than 0 in the first place, right? So if probability of B is equal to 0, then I have a kind of a divide by 0 problem, right? So this hopefully makes sense, and you can see that this actually is very useful in real life because of the way that events sometimes are correlated together, right? So sometimes we get a lot of information. So for example, suppose these are the events A and B, and I tell you, okay, I saw B, what's the probability of A? I can immediately say that's equal to 0, right? Because these two events have no intersection. This is like saying, okay, you know, I know that the suspect was wearing a red jacket and this guy is wearing a green jacket, right? So seeing B immediately rules out A. Or kind of the opposite of that is saying, okay, this is the event A and this is the event B. In this case, if B happens, then A happens with 100% certainty, right? So this is like saying probability of A given B is 1. The reason is that you know, the probability of A intersect B over probability of B is itself the probability of B over the probability of B, which is 1, right? Another case where this is useful is something like this, where I have A and B, and I'm drawing these really small. So A and B by themselves are both super unlikely, right? They're very, very rare events. But if I see B, it gives me a lot of information about whether A happens, right? So this is like saying the probability of A given B is big, even though PA and P of B by itself are both small, right? For example, I am testing for some super rare disease, and there's a super rare symptom that you hardly ever see, but when you do see it, it basically indicates for sure that the patient has this disease, right? So these are the cases where conditional probability helps me out a lot. Of course, there are cases where seeing B doesn't tell me anything about A. So for example, I have this situation where let's suppose that A is the top half of the rectangle, and B is the left half of the rectangle. And now I can ask, what's the probability of A given B? Well, these two intersect in this region, right? And so the probability of A given B is the probability of their intersection over the probability of the whole thing, which in this case is, let's assume that this is a unit square, okay? So here, the area of this red part is 1/4. The area of B by itself is a half. So 1/4 over a half is again a half. And here in this case, I can see that this is in fact the same as the probability of A, right, which is the area of the top part. So this is like saying, I saw B, but it doesn't actually really change my underlying probability of A, right? B provides me with no new information about A. So that can happen sometimes, right? So let's do a couple of quick examples. So let's suppose that I look at my kind of typical probability rolling of 2 dice, okay? So I've got the possible die rolls, and I've got the possible sums. So let me quickly jot down this table. So what I'm looking at here is the sum of the 2 dice. Okay. So hopefully, as you know from rolling dice, 1 is unlikely and 12 is unlikely and 7 is the most likely thing. Okay. Don't worry about my head blocking this. We're not going to use that number. Okay. So I could ask a question like this: what's the probability that the if I call this die roll number 1 and die roll number 2, what's the probability that the second die is even, given that the dice sum to 4? Okay. Well, we have 2 events, right? Event A is second die is even. Event B is dice sum to 4. And event A intersect B is both of those things happening, right? So what is the probability of B by itself? We're going to need that. So that's saying that I have these 3 possibilities over the 36 total outcomes, right? So I have 3 good outcomes over 36 total outcomes is 1/12. Okay. What is the probability of A intersect B? That's saying that the second die is even and the dice sum to 4. So this is the second die here, and this square is the only event that is in both A and B. So this is like saying, okay, well, there's only 1 good outcome out of 36. And then the probability of A given B is the intersection 1 over 36 divided by the event B, which is 3 over 36. So this is going to be 1/3. Okay. And in this case, I can say, okay, well, what was the original probability of A? The original probability the second die was even. Well, if I just look at the second die by itself, I have 3 even numbers out of 6 total outcomes. And so here, I can see that observing that B happened actually reduced the probability that A happened, right? Because only one of these 3 outcomes is, satisfying that the second die is even. Again, you can kind of pick this off visually just by looking and saying the square makes up 1/3 of the total outcomes in B, and that's definitely a reduction in probability over A. Or I could say something like this. Let's keep this on the board and ask, what's the probability that the sum is greater than or equal to 8, given that one of the dice is greater than or equal to 4, right? So kind of intuitively, we can imagine that we think this should be kind of a good large number, because if one die is already large, then probably the sum is going to also be pretty large. So what's the probability of, again, this is event A, this is event B. So what's the probability of B? One die is greater than or equal to 4. Well, that basically means that I am in, I'm going to draw my things with a red pen to distinguish the second example. So that means that this die is greater than or equal to 4. I'm sorry, this is 3. This die is greater than or equal to 4. This die is equal to 4. So basically, all this stuff in this red box here is B, right? And so here, I can see this probability is 3/4 of the total outcomes. What's the probability of A intersect B? That's like saying, in how many of these cases is the sum greater than or equal to 8? That means I'm looking at these outcomes here. How many of them are there? There's 5 plus 4 plus 3 plus 2 plus 1. There's 15 out of 36. So what's the probability of A given B? It's 15 out of 36. over, and to make my life easier, I'm just going to say there's 27 out of 36 of these outcomes, right? I just multiplied both top and bottom by 9, and so I get 15 over 27, which is equal to 5 over 9. So I can see that once I know that one of the dice is greater than or equal to 4, it makes the probability that the sum is larger to be a reasonably large number. Okay? And I could do the same thing in the continuous world, right? So let's suppose, kind of carrying on the example from the last mini lecture, for continuous sample space, the setup is I pick two numbers, x and y, randomly in 0, 1. And I want to know what's the probability that y is greater than x given that y is greater than a half. So the way I would do this would be to draw my box of x and y. So what is my event B? This is A, this is B. Right? So the probability of B is the probability that y is greater than a half. So here's my sample space, and here is the probability of y being greater than a half. I can see immediately that number is half of the total square, right? What's the probability that of A intersect B? So now I have to say, where is the event y is greater than or greater than x? So here's the line x equals y. The probability of this intersection, I have to look at what is the event like this, right? And then I'm looking at where both of these things occur. So really, I'm looking at this intersection event here. What's the area of this black part? I know I could have done this better, I'm sorry. Well, the area of this thing is half, so I can kind of reason that each of these little triangles that make up the whole thing must be an eighth. So I can see that this dark part is 3/8, and so the probability of A given B is 3/8 over 4/8 is equal to 3/4, right? So again, telling you that y is greater than a half increased my probability that y is greater than x, right? Because if I look at this y is greater than x, I can see that this A by itself has probability of half. Now I tell you, hey, y was already pretty large. That makes it much more likely that y is bigger than x. Okay, so this is kind of a conditional probability case with continuous values. Okay, see you next time.